unfold.
Today, we're not just looking up at the stars. We're popping the hood on reality itself. We're going to ask a wild question. Is our universe the one and only real thing, or is it more like an operating system? Welcome to our deep dive, the cosmic kernel. So let's just jump right in, shall we? The biggest question of all, is any of this real? I mean, the feeling of the chair you're sitting on, the taste of your last meal, the very thoughts running through your head right now, are those things fundamentally, physically real? Or are they being rendered for you, like a scene in the world's most advanced video game? Okay, I know what you might be thinking. This sounds like something straight out of a sci-fi movie. But hold on, this isn't about fan theories or wild speculation. We're going to approach this like a serious investigation, a forensic audit of reality's source code.
Yeah, that's right. We're going to be cosmic debuggers. We're setting aside all the usual stories about how the universe began. For today, let's treat the universe like an engineered piece of technology. And if it was engineered, that means it has rules, it has limitations, and maybe, just maybe, it has a few glitches we can find.
Our audit doesn't start with a particle accelerator or a super telescope. Nope. It begins with a piece of pure logic so sharp and unforgiving, it's been called a statistical guillotine. We're starting this case with cold, hard probability. Back in 2003, a philosopher named Nick Bostrom laid out this brilliant argument called the simulation trilemma. It's basically a logical trap. It forces you to conclude that one of three very specific, very wild propositions about our reality is almost certainly true. So what are these three possibilities? All right, number one, doom. It means civilizations like ours, any civilization really, always destroy themselves before they get smart enough to run super realistic simulations of their own past. Number two, boredom. Any civilization that does become that advanced just loses interest. They have better things to do than simulate their primitive ancestors. And then there's option three, simulation. If the first two are false, then you are almost certainly living in one. And here's where the logic just grabs you. It's totally ruthless. If we manage to not drive ourselves into extinction, and if future humans, or whatever we become, are still curious enough to run these ancestor simulations, well, then that third option becomes pretty much a mathematical certainty. Why? Just think about it. A civilization that can run one perfect simulation isn't going to stop at one. They'll run thousands, millions, billions of them. So for every single base reality, there would be billions of simulated realities. Now do the math. What are the odds that you, yes you, happen to be in that one single original reality? The probability just plummets. We're talking 1 in billions. Okay, so the statistics are pretty mind-bending, but logic isn't physical proof, right? So for our next piece of evidence, we need to go looking for actual glitches in the source code. And to do that, we have to start reinterpreting the laws of physics not as laws of nature, but as the system limitations of a giant computer. Think about your TV screen. You can get closer and closer, but eventually you're just looking at a single pixel. You can't zoom in any further. Well, what if the universe is the same? It turns out it is. There's a fundamental limit called the Planck length. It's like the pixel size of reality. Below that, our concepts of space and distance literally break down. And once you start thinking that way, the translations from physics to computer science are, well, they're kind of spooky. What we call space-time, that could just be a giant 3D grid of pixels, or voxels. The Planck length, that's the resolution of the grid. And the speed of light, the ultimate speed limit of the universe, well, that looks a lot like the maximum processing speed of the system, the fastest that information can travel from one point to another. This brings us to probably the weirdest, most baffling part of modern physics. And it's something that suddenly makes a whole lot more sense if you're thinking like a programmer. Why on earth does reality seem to wait until we're looking at it before it decides what to be? It's the famous observer effect in quantum mechanics. When a particle isn't being measured, it doesn't really have a definite position. It's just a smear, a wave of all the places it could be. But the very instant you measure it, the moment you observe it, poof, that wave of possibilities collapses into one single concrete particle in one specific place. It's almost as if the universe only bothers to render the details when you demand to see them. And if that sounds familiar, it's because video game designers have been using this trick for decades. It's called lazy loading.
To save precious processing power, a game engine only renders the high-detail graphics that the player is actually looking at. The stuff behind you, it's low-res or maybe not even there at all. From this angle, quantum collapse starts to look less like a deep cosmic mystery and more like a really clever optimization to save on resources.
And then there's quantum entanglement. This is the thing Einstein absolutely hated. He called it spooky action at a distance. You can link two particles, then send them to opposite ends of the universe. The moment you measure one, its partner instantly knows and takes on a corresponding state. Faster than light. It seems to break the most fundamental rule of the system. But you know what? In computer science, this isn't spooky at all. In fact, it's a pretty basic concept called pointer aliasing. Think of it like this. You have two different shortcuts on your computer desktop, but they both point to the exact same file. If you use one shortcut to change the file, the other one sees that change instantly, because they're not two separate things. They're just two pointers to the same chunk of data in memory. The distance between the shortcuts is totally irrelevant. So this brings us to our last line of evidence, and honestly, this is where it all gets seriously strange. We're moving beyond just interpreting physics as if it were code to finding what looks an awful lot like literal computer code woven into the very fabric of reality. So there's this brilliant theoretical physicist, S. James Gates, Jr. He was deep in the mathematical weeds working on the equations for something called supersymmetry, and he stumbled across something that it just didn't belong. He found error-correcting codes. I'm serious. Specifically, a type of binary code that's used to find and fix errors in data transmission. This is the exact same class of code that your web browser is using right now to make sure the data it receives from a server isn't corrupted. It leaves you wondering, why would the fundamental laws of the universe need a data integrity check? And this isn't just my interpretation. The discovery was so shocking that Gates himself, the man who found it, said this, and I quote, "I'm left with the puzzle of whether I'm looking at matrix code. It's like finding the architect's signature, a system designed to keep the simulation from crashing." And there's more. There's a newly proposed law of physics, some are calling it the second law of infodynamics, and it basically says that over time, information systems tend to become more orderly and compressed. In other words, the universe seems to be constantly trying to optimize its own data, a bit like running a zip file on itself. And that's exactly what you'd expect from a system trying to save on storage space.
So, if the math, the physics, and the embedded code are all pointing in this one bizarre direction, we have to face the final and, frankly, pretty chilling implication. Let's talk about the termination risk. What happens if the admins of the simulation realize that we're onto them? Well, the philosopher Preston Green has warned that if we are in an experiment, let's say a simulation to see how a civilization develops, then the moment we discover we're being watched, we contaminate the results. Our behavior is no longer genuine. And what do you do with a contaminated experiment? You shut it down.
And that leaves us with the ultimate question, doesn't it? Do we keep pulling at these threads? Do we keep searching for glitches in the code, trying to get the attention of whoever or whatever is running this thing? Or is the smartest, safest play for our own survival to just quietly play the game and hope we never cause an error big enough to force a system reboot?